Good morning, everyone. Just a thumbs up or hold up your hand if you can hear me. I just want to know if you can hear me. Just a simple mic check. Clifford, Sulwetu, can either of you hear me? Guys, thumbs up if you can hear me, or just any indication that you can still hear me. Lucia, since you've just joined, can you hear me? Just give me a thumbs up if you can hear me. Thank you, ma'am. Okay, can you see the screen that I'm sharing? Okay, thank you. Now you are guys are currently busy with resistance and circuits. Okay. Now don't. This is going to be a relatively short session. Don't worry about the numbering of the questions. You should worry about the content of the questions themselves. Okay. So I'm not going to waste yours or my time. Let's just head into the questions and then discuss them as we go along. Don't worry about the numbering, like I just said. You just worry about the content of these questions, okay? Because a lot of these questions you're going to see them again, oh, in various forms. Okay, now let's take a look at this question. Okay, let me just see. Okay, so you can still see there. So let me move back. Let's take a look at this question. It says 5 joules. Uh, is that the entire question? Let me just see. Oh, it should not be if, it should be off. Okay, that's why I'm wondering if it's the entire question. Okay, so 5 joules of work is done in moving 12.5 times 10 to the 18 electrons from one end to the other end of a conductor. Okay, so we have a conductor and they are moving electrons are being moved from one end to the other end of the conductor. Okay, and they're telling us that 5 joules of work is done in moving these 12.5 times 10 to the 18 electrons. So 12.5 times 10 to the 18 electrons. That's a lot of electrons. Okay, are being moved from one end to the other. Now that is basically how electricity flows. Okay, it flows a bunch of electrons moving through a conductor. Okay, now they ask us what is the potential difference between the two ends of the conductor. Now, first of all, how do we calculate potential difference? Okay, potential difference is nothing but the amount of work done to move a certain charge. Okay, it's joules per coulomb. Okay, that's how we get its units of joules per coulomb. Okay, because work is measured in joules and charge is measured in coulomb. So it's work done per unit charge. So that is voltage. Okay. They want the potential difference or the voltage between the two ends of the conductor. Okay. Now we already have the formula to calculate the potential difference. That formula is, I'm going to give it again, it's work divided by the charge. Okay. Now, do we have the charge? Okay. We have the work. They tell us it's 5 joules. Okay. Do we have the charge? Anyone in the audience would hazard a guess? What is the charge? How can we get the charge? How can we get the charge? We have the work. We want the potential. How can we get the charge? Do we even have charge? Okay, so the charge, remember this. Okay, remember this. Charge is quantified. Okay, there is a smallest unit of charge. Okay, and that is the charge of an electron. Okay, now, since we are moving 12.5 times 10 to the 8 electrons, how much charge are we moving in that time period? How much charge is being moved? That's easy then. We take the 12.5 times 10 to the 18. This is the amount of electrons that we have. Okay? And we multiply it by the charge on a single electron, which is 1.6 times 10 to the negative 19. Let me try to put it in there. This is the amount of electrons that we have, and this is the charge on a single electron. That last part can't fit in. Let me rewrite the whole thing. We have a charge, or rather we have 12.5 times 10 to the 18 electrons in total. Multiply that by the charge on a single electron, 1.6 times 10 to the negative 19. And that, ladies and gentlemen, gives us the total charge that is moved throughout this conductor. It's just the number of electrons multiplied by the charge on a single electron, and that will give us the total charge for all of those electrons. Okay, now if you multiply 12.5 times 10 to the 18 by 1.6 times 10 to the negative 19, you get 18 minus 19. That is negative 1. 12.5 times 1.6. 12.5 times 1.6, that should be around 20 or somewhat. And then you divide that by 10. Well, anyway, you can do this whole thing on your calculator. You should get 2,0025 coulombs. This is the amount of charge that is being moved through this conductor that we drew earlier. Okay, remember we have a conductor, and in this conductor we are moving charges from one end to the other. Okay? And the amount of these electrons, which is a charge, the amount of those electrons is 12.5 times 10 to the 18 electrons, with each one of them having a charge of 1.6 times 10 to the negative 19. Now we have the total charge of all of those electrons. We can then work out, using the formula that we've been accustomed to right now, we can work out the potential difference, which is just the work divided by the charge. Okay, and in this case, the work is 5 joules and the charge is 2,0025 coulombs, which means 5 divided by 2, basically 2,0025. If we take that, it's approximately 2, let me write it on the next. If you take this answer, we go to the next page. That answer is approximately 2.4, or rather 2.5. Let's just make it 2.5 instead of 2.49. It's approximately 2.5 joules per coulomb. And another way of saying joules per coulomb is 2.5 volts. That is 2.5 volts. That's the potential difference between the two ends of the conductor. Okay, that's a nice problem to wet our beaks. So remember, in this case, to solve this problem, you needed to know that voltage is defined as the amount of work done to move a charge. That is the crux of this problem. You needed to know this particular formula. Okay, and make sure you know it. And let's just check here. They give us some options. We've calculated it is 2.5. We can check. And the correct answer is 2.5. Question number 12. Like I said before, don't worry about the question numbering, worry about the content of the question. Number 12. Here we have, they tell us there's a well-insulated electric water heater. Okay, a well-insulated electric water heater connected to a 240 volt potential difference warms 109 kilograms of water from 20 degrees Celsius to 49 degrees Celsius in 25 minutes. Basically, this thing is describing a geyser, okay, a water geyser. It is well insulated. It has insulating material in between those metal strips. Those tin, I don't know if it's tin or zinc that they use to cover it. I think it's zinc. And in there they have insulating material, and it's connected to a 240 volt potential difference, meaning it's plugged into 240 volts, and it warms a mass of water from 20 degrees Celsius to 49 degrees Celsius. So 109 kilograms of water is warmed from 20 degrees Celsius to 49 degrees Celsius in a time span of 25 minutes. Okay, so this is all that we've been given so far in this problem. How do we go about, or at least first of all, let's find out what do they want? What is the resistance of the heating element? Okay, so they ask us what is the resistance of its heating element. Now, in order for the water to be heated up, it needs some sort of resistance, okay, some sort of element. In a kettle, we have that element at the bottom. In old kettles, they used to have that round ring element that looks like a spiral. Nowadays, it's just a tin, but the element is underneath of that, below that. So we have this element. It's inside the water and it's slowly heating the water. Okay. Now that cannot happen. That heating process cannot happen or cannot occur if there is no resistance in that element, in that heating element. Because if it had no resistance, the current would just flow through it. Okay, it needs resistance, and once it has resistance, it begins to build up and it heats. Okay, so they want what is the resistance of that heating element, and they tell us to use the specific heat capacity of water as 4186 joules per kilogram degree Celsius. Now we all know that that's the highest naturally occurring specific heat capacitance. Now, first of all, we need to determine they want the resistance of the heating element, right? Let's start working backwards. Okay, how are we able to get the resistance of this heating element? Okay, We can get it using the formula power is equal to the voltage divided by the resistance. Okay, this is the resistance that we want. The voltage we have been given, or rather, yes, this is the voltage we've been given, but we want the power. Okay, we want power, the power of this water heater. Okay, so, and now in order to get the power, what is power? Power is equal to, let me just see if there's any questions yet. We know that power, remember we want, let me just go back. This is the formula that we can use to calculate the resistance of this heating element. Now we want the resistance, we have the voltage. So can we calculate the power? Let's see. What is power defined as? Power is defined as, you should know all of these formulas. Power is defined as the amount of energy per unit time. Okay. Now in this formula, we can get the power, but we have the time, we need the energy. Okay. We need now the energy. Okay. So how do we get the energy? You see, we're working backwards. I'm working backwards to see how can we start this problem by looking at what do we need to calculate first. We need to get, well, what do we need? We need to calculate the resistance. There is one formula, this particular formula, that can give us the resistance because it's in terms of voltage which we have. Now, it is also a formula for power, but we don't have the power. But can we calculate the power? Yes, we've been given time, so we can calculate the power. But in order for us to calculate the power, we need to calculate, first of all, the energy required or the energy that is used. Now, how do we calculate the energy? You see, once we have the energy, we can calculate the power, and from the power, we can calculate the resistance. Okay, it's flowing. I'm just thinking from what we want, moving backwards to how we can start the problem. Okay, so what is energy? How do we calculate energy? You know this from, okay, that's not delta T. From your first semester in thermodynamics, we have that energy is nothing but mass times the specific heat times the change in the temperature. Okay, so now we have all of the formulas. So we can now calculate the resistance, okay, because we have everything. We have the change in the temperature, we have the specific heat, and we've been given the mass. So we start from this formula. This will be number one, this would be number two, and then finally we can work out number three, the resistance of this heating element. So just checking here, everything seems to be fine. I can still see you guys on Teams. Okay. Now, let's start off. First of all, let's calculate firstly the change in the temperature. Okay, the change in the temperature is what we need first. Okay? So the change in temperature is just the T final minus T initial, and that is equal to 49 degrees Celsius minus 20 degrees Celsius. So now we have the change in temperature, which in this case is 19 degrees Celsius if my math is correct. Oh, sorry, not 19. It's 49. So it should be 29 degrees Celsius. So there we have the change in temperature. Okay. Now using this change in temperature, we can now calculate the energy that is being used by this water heater. Okay. The energy that is being imparted from the amount of energy used by the water. In other words, that should be the same amount of energy that is created by the element. Okay, so the amount of energy used by the water is just mass times specific heat times the change in temperature. Okay? The mass, we are told that it is 109 kilograms of water. So 109 kgs of water. The specific heat of water we have been given as 4186. Did I just remember that correctly? Yes, I did. I'm not going to write in the units. I might not have space at the end. And then finally, the change in temperature is 29 degrees Celsius, which we just worked out. Okay? And if you multiply all of these together, now I usually don't do the multiplication part like physically go on a calculator and show you how to multiply. I assume you all know how to multiply 109 times 4186 times 29. You can plug that into your calculator, but you will get the following. And I wrote it down as I got it: 132,499, and then it's 94, right? Joules. Or you can just say 1 comma 3 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7 joules, right? If you want to write it that way. So now we have the amount of energy that the element produced. Okay, so this is what the heating, this is the amount of energy that the element produced. Okay, now using the amount of energy that this element produced, remember it didn't just produce it in the snap of your fingers by or in a blink of an eye. It produced this amount of energy over a period of time. Okay, and that time that it produced this energy is 25 minutes. Okay, so how many seconds are there in 25 minutes? Let's just check. In 25 minutes, the time. We write temperature with capital T. Let's say for time, we denote it small t. Time is equal to 25 minutes with an ugly 5. It's 25 minutes of time. It produced that amount of energy in 25, 1.3 times 10 to the 7 joules in 25 minutes. That's the amount of energy it produced. But we want it in seconds because when we use power or we calculate power, we use seconds. And it's the SI unit for time. So 25 minutes, and how many seconds in 1 minute? There are 60 seconds per minute. Minutes will cancel. 25 times 60 gives an answer of 1,500 seconds. So there's 1,500 seconds, or 1.5 times 10 to the 3 seconds. So this what 1,500 seconds in 25 minutes. Okay, so now we can calculate the power. Power is equal to the amount of energy produced by the heating element divided by the time over which it produced this amount of energy. So the energy we've already written down as 132. Let me just read it correctly. 499 and then 94 joules. This is the amount of energy that's produced by this heating element or this heating coil, and it produces this energy over a period of 1500 seconds. And a joule per second is what? That old joke. A joule per second is a watt. A 1 joule per second is a watt, and it's a unit of power. So 132,499,994 divided by 1500 is equal to approximately 8,83. 8,833 times 10 to the 3 watt. So this is the amount of watts, or this is the power that is generated by this heating element. So this heating element is generating this amount of power. So now we have the power. And if we continue, we can now calculate power. We know power is equal to voltage divided by the resistance. Okay, and remember the whole uh, uh, reason for this question is so that it can get this resistance. So this resistance, therefore, that resistance is equal to the voltage squared, which we've been given, divided by the power, which we just calculated. So the voltage is, remember, it's 240, I think. 240 volts, yes. 240 volts. We square it. Don't forget to square it. And we divide by the power, which we just calculated as 8,8333 times 10 to the 3 watts or joules per second. And that gives us an answer in ohm. And it is the resistance of this particular heating element. It has a resistance of 6.53 ohm. That's the resistance of this heating element. Now, here's a question for you. Okay, if we want to say, if we increase the resistance of this element, okay, what's going to happen to the time it takes to heat this water? Okay, let's say we increase the resistance. If we increase the resistance, just look at this formula. If the resistance is increased, the voltage and everything else stays the same. If the resistance increased, the power will decrease. Okay, and we remember power is equal to that divided by time. If the same energy is being controlled and if the power decreased, the amount of energy will increase. Okay, the amount of energy, heat energy being put out will increase. For the same time period, the amount of energy will increase. And if the amount of energy increases, the temperature of the water will be higher. Okay, so that's the way you can think about these things in terms of formulas. Okay, what happens if I keep all of them constant and increase this and that? Okay, it's a good exercise to do. Let's move on to question number 13. Okay, by the way, let's just check what was our answer again. It was 6.53. Let's check 6.53. Bam. The correct answer is 6.53 ohm. Question 13. Question 13. Some of these questions are very fun. I had a nice time just working them out. Nostalgia to my first year in physics. Okay, now we have two light bulbs. Let's say we have two light bulbs. Okay, they both operate on a 120 volts. Okay, this is the, please note this type of problem here. Okay, they always like to include it because they want to see if you can think logically. Okay, two light bulbs. Let me just put it nicely there. Two light bulbs operate on 120 volts. Okay, so these two light bulbs operate on 120 volts. One has a power of 25 watts and the other 100 watts. So we have two light bulbs. They both operate on 120 volts. One has a power of 25 watts and the other has a 100 watt bulb. Which light bulb has a higher resistance? Which light bulb has a higher resistance? Okay, now you can work this out. Okay, how do I calculate? First of all, they give us power. So what is power? We saw in the previous formula the power is V squared over R. Okay, Now they give us the power and they tell us the voltage. They want to know which one has the higher resistance. Okay. Now, in order for us to calculate that, we just make resistance the subject of the formula. Resistance is therefore equal to voltage squared over the power. Okay. Now let's do this one for. Let me rather write that. Oh, I can just keep that rather. Therefore, resistance is equal to voltage squared over power. So for the 25 watt bulb, so for the 25-watt bulb, let's calculate its resistance. That is 120 squared divided by the power is 25, and that gives us an answer of that's 120. So 12 squared is 144 times two zeros squared. That's 1144 and two zeros divided by 25, and that gives us an answer of, or it should give you an answer of 5,700 576 ohm. That's the resistance of this 25 watt bulb. Now let's check the resistance of the 100-watt bulb. That's 120 volts squared over the power. Now 120 squared we know is 14400. V squared, that's V squared, volts squared. The power in this case is what? And the power is 100. That is 144 ohm, if I'm not mistaken, if my math is not failing me. It's 144 ohm. That's the resistance of the 100-watt bulb. Now they asked us, which light bulb has a higher resistance? Which one has a higher resistance? It is the 25-watt bulb. It has a higher resistance. Okay, the 25-watt bulb has a higher resistance. So the 25-watt bulb has a higher resistance. Let's go check. We should always check our answers. Okay, the dim 20, we don't have a dim. None of them. Power does not depend on the resistance. It does. The bright 100 light bulb, both are the same. The same. Yep, there. The dim 25 light bulb. Let's check. They call it a dim. Why? Because it isn't. It doesn't have as much power. It doesn't produce as much light as the 100-watt light bulb because it has a higher resistance, or a, sorry, excuse me, not a higher resistance, a lower power output. Okay, power is the amount of energy that something produces per unit time. Now let's say for 10 seconds, for 1 second, a 100-watt light bulb would produce 100 joules of energy, while a 25-watt bulb will produce 25 joules of energy in 1 second. So it will be dimmer. That's why they say the dim 25-watt. And that's a very nice question. There is another one that they always ask like this, but it is a simultaneous question. Okay, this one is pretty straightforward. Just test if you know your formulas, and you should know this formula for power, or you should know all of them. Okay, power is equal to voltage times current, but voltage can also be written as I times R times that I, because voltage can also be written like that. So your second formula for power is I squared times the resistance. Okay, now we also know that voltage In this case, I can be written as volt over resistance. Therefore, it's V squared over R. So these are the three formulas for power. Actually, it's one and the same formula. It's just different ways of calculating the circuit for power. Okay. Now, question 40. Okay. This is a very nice question. Is it the one I just, okay, it's that one. 14 is, yeah, here's my page for question 14. Yes, I have it. So, in the circuit below, assume that the resistors and batteries are identical. Okay. If there are any questions at this point, please ask me. If you don't, then I assume you are following. In the circuit below, assume that the resistors and batteries are identical, so they have identical voltages and resistance. Which circuit or circuits have the greatest energy delivered to them per second? Now, what is energy per second? What is energy per second? Energy per second, let's write it as it sounds. Energy, which is work per second, or let me not use work. Energy per second, energy per unit time is what? Power. That is energy per unit time. Okay, the amount of energy per unit time is nothing but the power. So that gives us a hint. We have to calculate which one has the greatest power delivered in the circuit. Now we know, or we've established right now, that power is equal to voltage over resistance. Okay. Now let's work out the power for each one of these circuits. Okay. For the first one, let's look at circuit number one. Let me see if I can just make it a slightly bit smaller. Okay. Okay, that's circuit one. Okay, the one on your screen is circuit one. Let's see if you can see it. Let me just make it a slightly bit smaller yet again. Okay, there it should be fine now. There's circuit one. Okay, so let's work out the power for circuit number one. For circuit one, let's work out the power. Power is equal to voltage squared over R. Now, what is the voltage in this case? The voltage in this case is just normal V. Okay, we just call it V. It's some voltage, we call it V because they're the same for all of them. And then the resistance is in series. Note this, the resistance is in series. They are coupled in series. How do we calculate the resistance in series? We just add the two resistance. Let's call the resistance R. Okay, so if we add them, the total resistance would be 2R. Okay, so therefore the power in this case would be a half times V squared over R. It's a half V squared. I see it's going off the page there. It's V squared over R. It's a okay, let me just move it closer. I'm just taking out the half, then writing V squared over R. Okay, so that's the power produced in the first circuit. Let's check the power in the second circuit. Power, oh no, not resistance, power is equal to V squared over R. Can someone please tell me, anyone that is listening, I want to see if you know this. Those two in circuit 2, the batteries are connected in, let's say the potential on each battery is V. We've assumed each resistance is just R and each voltage is just V. Can you guys tell me what is the voltage of two batteries connected in parallel? Two batteries connected in parallel. What is its voltage? Anyone? Have you ever done with a situation, or have you ever dealt with a situation where you've been given the batteries are connected in parallel? Is there anyone here that can tell me what happens if two batteries are connected in parallel? Anyone? Okay, then. But note, when batteries are connected in parallel, okay, the total voltage will always be the same. Okay, it will be the same. It will be just V. Now the next question, your next question should be, but what if the batteries, in this case, the batteries are two of the exact same kind. They are both, they have the exact same voltage. Okay. Your question, then I told you that the voltage would just be the voltage of one of them. Your next question then should obviously be, what if those two batteries are not the same? And the answer is, we never ever deal with that situation. It's a bad idea connecting batteries of different voltages like this in parallel. So, for all of your problems, if you ever see them, the batteries will always be connected. If they are connected in parallel, the batteries will have the exact same voltage. You see, the problem that occurs when those two batteries, technically, let me just answer this chat question. Uh, Soweto, Mr. Soweto, Pituka, you said, okay, let me just enlarge my screen here so I can read. The total current increase, but the voltage stays the same. It's just the voltage that stays the same. The voltage stays the same. So if the voltage, the current is dependent on the voltage. So if the voltage stays the same, the current will also stay the same. Okay? Please note that. Do you get that, Mr. Soweto? Okay. So please ever, if you are ever encountered in a situation where you have batteries that are in parallel, immediately assume they have the same voltage and that the total voltage of that entire parallel system for batteries only will be the exact voltage of one of them. Okay. So in this case, for circuit 2, the voltage is just going to be V because the voltage on one of those batteries is just V. So it's going to be V squared, and then the resistance is 2R. Remember, we calculate 2R. There are two resistors there in series, right? So basically, for all intents and purposes, circuit 1 and circuit 2 is exactly the same. Just make sure of my facts. Aha, V squared over R. Okay, let's look at circuit number 3. Circuit 3, there's circuit 3. In this case, a wonderful thing happens. The batteries are now in series. Can anyone hazard a guess? What's the voltage going to be for batteries in series? For batteries, if you connect them in parallel, we've already established it'll just be the potential of one of them. But what happens if we connect the batteries in, say, uh, series? What happens if we connect the batteries in series? Can someone hazard a guess? What happens if we connect the batteries in series? Anyone tell me what happens if you connect the batteries in series? Okay, let me just see if there's anyone typing. Thank you, Soweto. Uh, you are correct. The total voltage is the sum of the two individual battery voltages. Okay, good work there, Mr. Soweto. So we want to calculate the power. It's V squared over R. But in this case, the total voltage is 2V. Okay, remember it's 2V now because we are adding the batteries. Okay, when they're in series, we add voltages, but in parallel, we just take one of the voltages and we square that. It's 2V squared over the resistance is still 2R. The resistance is still 2R. Answer, that will be 2 squared, that's 4 over V squared. So 4V squared over R. So it's 4 divided by 2, that's R. 4 divided by 2 is nothing but just 2. So basically, this is going to be 2V squared over R. 2V squared over R. Now, which one has the highest power? It would be circuit number 3. And that also answers our question. Okay, because the question was, let's go back to the question, to the original question. In the circuit below, assume the greatest resistors and batteries. Assume that the resistors and batteries are identical. Which circuit or circuits has the greatest energy delivered to them per second? So which one has the highest power? And we've established it is circuit number 3. Okay, so let's check circuit 3 as an answer. Yes, the correct answer is circuit 3. Let me just enlarge the questions again. Okay, so we are done with question number 14. It was a nice one. 15. Okay. And Mr. Solwetu, thank you for the participation there. Okay, now they're asking us, and you will get, I can guarantee it, you will get a question like this. What should be the bill? Meaning, how much should you pay? Remember, we are measuring electricity at our houses in kilowatts per hour. Okay, so what should be the bill for a month of June, which has 30 days, for a heater? Now, this is just a bill for the heater, and it's not every appliance, not your total. So, what should be the bill for the month of June for a heater of resistance 60.5? So, we have a heater, it's on for 30 days, it has a resistance of 60.5. Remember, the more energy, stuff like kettles and heaters and geysers should have high resistant elements so that they can produce the heat. So we had a heater of resistance 60.5. It's connected to a 220 volt main. Okay, so a main power supply of 220 volts. Assume the cost of energy is at the rand, 1 rand. It's it's at 2 rand. It is at what? Rand 2 per kilowatt. Okay, so 2 rand per kilowatt. And the heater is used 3 hours daily. Okay, so let's calculate some. First of all, let's do some base math. This is just the problem of calculating. Firstly, let's calculate the power. Okay, we know power is V squared over R. Okay, the voltage is 220. They gave that to us, 220 volts, and then the resistance is also given as 60.5 ohm, named after George Ohm. Okay, so then therefore the answer, if you do that math, 22 times 22 is 484, and then you just take on two zeros and you divide it by 65, you should get 800 watts. The power that this thing produces, this heater, is 800 watts of power. It produces 800 watts. So basically it produces the same amount of energy as eight of those, remember those 100-watt light bulbs? So it produces the same amount of energy in a second as eight of those bulbs would. Okay, so 800 watts of energy of power is produced by this heater. Okay, so we've calculated how much power it produces. Now let's do how much energy is being consumed. Okay, in watts per hour. Now let's calculate the amount of watts per hour for one day. So a daily consumption, it is connected for 3 hours every day. So it's on, basically, they tell us it's on for 3 hours every day. So the energy produced or the energy consumed, let's first write there, energy consumed, energy consumed daily. This is for a day or per day, is the 800 watts, and you multiply that by the amount of hours it's on for per day, which in this case is 3 hours. Okay? And that gives us 800 times 3, that's 888, that's 240 or 2400 watt hours. Okay, so that's the amount of energy that it consumes in one day, 2400 watt hours. Now we want it for the entirety of June. Okay, and they tell us the energy consumed, that's daily, this is energy consumed monthly, this is per month. So we have the 24 watt hours that we consume, 2400 watt hours per day. And how many days are there in June? They told us there is 30 days in June, times 30 days. 30 days. There's 30 days in June. And that gives us 72,000 watt hours. So we have 72,000 watt hours that is being consumed in one month. Now, if we divide this, or we can also write this into something that you may find a little bit more familiar, it is 72,000. We can also say 72,000 watt hours. We can say 72,000 kilowatt hours. That just means 72 times 10 to the 3. Remember, kilo is to 23, and you may have heard of the word kilowatt per hour, kilowatt hours. Okay. Now let's calculate the cost. And do you know why I converted also to kilowatt hours? Is because our cost per hour is given is 2 rand per kilowatt hour. Now how do we calculate the bill? Let's calculate the bill now. The amount of money that you need to pay. The bill is equal to 72 kilowatt hours that we've used throughout the month. And how much is it per kilowatt hour? It is 2 rand. Oh, we write the rand symbol before the 2. It's 2 rand per kilowatt hour. So kilowatts cancel. 72 times 2, that's 144, right? So it's 144 rand in the month of June to keep the heater on for 30 days, 3 hours per day. That's how much it costs. So you'll spend 144 rand on the heater's energy alone, right? In winter. And I hope everyone understood that question, because you are going to see one like it or the same question, but you will definitely see another one. Reason being because it is one of the most applicable type of questions we have, because we all use electricity in our daily lives. Some questions they will ask you, which of these is more effective? Which of these uses more energy, the refrigerator or that? If given the power of the refrigerator is this and that. Okay, you will see quite a few of those questions. Now let's move on to the next question. This one I had. Let me just make it smaller quickly. I want to fit the whole thing in there. Okay, there it is. The whole circuit. The question is, assuming the two resistors, okay, assuming these two resistors here, there's a resistor and there's another one. Assuming those two resistors are identical, meaning they have the exact same resistance. Okay, rank the current. Okay, the currents in these points 1, 2, 3, 4, 5, and 6 from the highest current to the lowest. Okay, so where will the current be the highest and where will it be the lowest and where will it be equal to the others? Okay, this is an easy question. First of all, is there anyone here brave enough to attempt this question? Which current, can I ask you guys, which current, at which points will the current be the highest? Those of you that are brave enough to hazard a guess, where will the current be the highest? Right? This is question what again? I don't really care about the numbering of the questions. 16. You shouldn't care about the numbering either. Just worry about the content. Okay. Can anyone hazard a guess? And please note, let me just move it up again. Okay. If can anyone hazard a guess at what point will the current be the greatest?
5 and 6.
5 and 6. Okay. Mr. Tandiwe, was that you speaking? I can't see you, but I did see your screen light up for a minute.
Yes, it's me.
Okay, yes, you are correct. 5 and 6 is the highest, has the highest currents. And 5 is equal to 6. First of all, 5 is equal to 6 because of Kirchhoff's law. Well, you'll do, I don't know if you've done it yet, but you will do. Uh, the current inside a circuit in series, or the current inside a circuit, is everywhere the same if it's in series. Okay? If it if the wires split in parallel, the current is divided. That's why we say parallel circuits are current dividers and series circuits are potential dividers. Okay? So the current will be exactly the same at 5 and 6, and these two currents will be bigger than all of the others because they are in parallel, meaning they've already split. And if you know Kirchhoff's law, you will know that at the point where it splits, I don't know if you guys can see my cursor or not. At this, okay, can someone just confirm? Can you see my cursor when I hold it over like my little arrow? Can you see it?
Yeah, yes, I can. I
Okay.
can.
Now at this point here, where the current splits, and at the other point here where it combines, at those 2 points, the current should be exactly the same. Okay, meaning the total current that goes into this parallel system should be the total current coming out. Okay, so since these two resistors are exactly the same, what do we know? The current is halved exactly. Okay, when the current splits into two, let me just draw it here. Okay, when the current splits, let's say current splits like this. Right? Let's say the current splits into these two. Okay, the current here, let's call it I1, and this one I2. Let's say this is the resistor here, and that's another resistor. The current at this point and the current at this point is exactly the same. Okay, and since these two resistors R and R are exactly the same, the current is split equally, meaning the current going in their direction there, I1 and I2, is also the same. Now, another thing you should know about currents going through a resistor, the current that goes into a resistor must be exactly the same as the current coming out of the resistor. I2, sorry, this one should be I2. The current going into a resistor should be the same as the current coming out of a resistor. But we've already established that the current I1 and I2 is also the same. Therefore, this current I1 is equal to I1, which is equal to I2 and I2. So, if we just go to the drawing, we know that due to the resistors being the same, the currents that are split 1 and is equal to, oh, I'm writing I here, 1 is equal to current number 3 because they go into exactly the same resistor. But we know that the currents that go into a resistor must be exactly equal to the currents coming out, meaning 2 and 4 are also the same. Okay, so 5 and 6 is bigger than 1, 3, 2, and 4. And that, let's see if there is an option for that ensemble. So 5 and 6 must be apart, they must be equal to each other. There's only two of them that says 5 and 6, it's D and E. And then the rest of them must be the same, all of them. That will leave only question number E. Let's check. Question E. Are we correct? Yes. The correct answer is 5 and 6 are uh, equal, and then the rest are equal. And then 5 and 6, of course, is the highest. Question number 17. There is one question that I keep. Okay. Oh, yeah. Consider the following circuit. Okay. That circuit there is a series circuit. We have a series circuit. Okay. Let's consider that circuit there. We have a battery, and then we have a light bulb, and then another light bulb, and then another light bulb. Excuse my messy drawing, and another light bulb. But what I want to point out is that all of these light bulbs are connected in series. And the question then which of the realistic circuits is represented by that circuit? Which of the following drawings is represented by that circuit? Can someone please hazard a guess? Look at those four circuits and then tell me which one of those circuits it can be represented by the drawing I just made there. I'm going to give you a few 2 minutes or so. Which one of them can be represented by that circuit I just drew? Yes, Mr. Solway too. Quick on the money, Mr. Shumani. Quick on the money. You guys are indeed correct. There is one circuit that can be represented by that drawing. It is circuit number 3. Circuit number 3. Okay, it cannot be circuit 1 or circuit 2 because they have parallel bulbs in parallel there. Circuit 3 is correct, and then circuit 4, the wiring is wrong for the second set of bulbs. Okay, so it is circuit number 3. So circuit 3, thank you guys there, quick on the money. Circuit 3, we're almost done. The rest is just two multiple choice questions, and then the last one is a question that you should all know how be able to do. Now, question number 18. They ask us if you double the current in a battery. Let's say you have a battery, okay, and you double the current that passes through the battery. Is the potential difference across the battery doubled? Is the potential difference across that battery also doubled? You guys, can you just answer your question? Whether you're right or wrong, does that matter? Okay, think about it. If you double the current that goes into a battery, okay, if you double the current flowing in a battery, let me draw the situation. This is a battery. Let's say you double the amount of current going in. Will the potential difference across the battery double? Because the current in the battery is now double. Will the potential difference double? Is it yes or no? This is a question that is tricky dependent on if you have heard of something called internal resistance. If you've never heard of it, the answer is yes. But if you have heard of internal resistance, and Mr. Soweto, you are correct, yes. If you've heard of internal resistance, you will know that if you double the current inside a battery, does not necessarily mean that the voltage will double. That is because a battery has something called internal resistance. You have done it in school. I know that because I used to teach in school. So the answer should be no, it will not double because the potential difference is a property of the battery itself. The potential difference is a property of the battery itself. And the reason we say that is because every battery has its own internal resistance. Finally, which of the following graphs, and that they don't have all of the graphs here in the example. Okay, there they are. Okay, so let me just make it smaller again. We have four graphs here. Okay, this is graph number 1, graph number 2. Let me just read the question. Which of the following graph represents an ohmic conductor? An ohmic conductor is one that represents, well, an ohmic conductor follows Ohm's law. I is equal to R. V is equal to IR. Okay. Now, which of these graphs represents Ohm's law? Okay. Is it the first one? This looks like a snake. Is it the second one? Is it the third one? Number 3. Is it the fourth one? Now note what I forgot to mention is on the horizontal axis we have the voltage, and on the vertical axis we have current. Which one of these best represents an ohmic conductor, meaning it follows Ohm's law? Can you guys hazard a guess? Which one do you think represents or follows Ohm's law? Which one of those conductors? Look at the formula for Ohm's law. V is equal to IR. Let me write it in another way. If you were to graph this would be Y. This would be your X value as it's written there. And then of course this would be M. and then plus 0. C in this case is 0. What is that? That is a straight line. Okay, meaning Ohm's law will have a straight line graph with the slope being the resistance. So it would be graph number 3. So graph number 3 is the answer. An ohmic conductor will be represented by graph number 3. And we're checking number 3, and yes, it's correct. The correct answer is 3. Then our final problem for today. Our final problem for today. If you have any
Hello,
questions,
sir.
okay, you can go ahead.
Yes, sir. Can you go back to question 19?
19, okay?
So,
Yes,
so, so it's not. So is it not a problem? I mean, the graph is not
yes.
always the current. It's a dependent variable.
Uh, yes. Remember, we are now talking about the ideal case. In the ideal case, it will always be dependent on those two, okay? Uh, those two will always be dependent. It depends on which one you measure, first of all. In this case, you can have the current as the dependent variable, okay? Or you can have it as an independent. You can, in this case, they made current the independent variable, and they just measured the voltage. Does that make sense?
Oh, okay. Oh, yeah.
It depends. You can choose in this case because you can measure either one.
Okay.
They just measured the current and then, well, they adjusted the current and then they measured the voltage. They chose how much current to let into a system and then chose to calculate the voltage, and it should give you a straight line. But
Okay.
that
So if voltage was the dependent, that means the the gradient would be would be one over r, right?
1 over
The
R, yes,
gradient.
yes. It'll just be the
Okay. Yeah.
inverse of the resistance.
Okay. Thank you.
You see, if you let's just go to that one. If we calculate the resistance of this graph here, okay, just check it here. It'll just be the change in I over the change in V in this case, okay, which is just going to be equal to 1 over R. Does that make sense?
Yes, sir. Thank you.
Okay. Okay, question number 20. Okay, this is the one that is probably the most, not difficult, it is just, yeah, it takes time because it's a simultaneous equation. Okay? It tells us, and this is a problem that you will see a lot. Well, not a lot, but it will test you if you know how to calculate resistance in series and resistance in parallel. This is what this question essentially does. See if you know the difference. Two resistors, they tell us that we have two resistors, okay? And they are connected in series first, and then they are connected in parallel. Now, if they are connected in series, how do we calculate the resistance in series? Okay, in series, let's say we have two resistors. They tell us there are two resistors, R1 and R2. Ugh, can't see that part. This is 20. We they have two resistors, R1 and R2, and they tell us they are connected first in series and then they are connected in parallel. Okay, the equivalent resistance, meaning the total resistance that you get if the two cases in if they are connected in series is 9 volt, meaning how do we calculate resistance in series? If they are in series, this is a series. If we add them in, if we connect them in series, we get the equivalent resistance as R1 plus R2, and they tell us in that case the equivalent resistance is 9, 9 ohm. But if we connect them in parallel, they say the equivalent resistance is 12 ohm. Okay, so in parallel, if we connect them in parallel, the resistance is 12 ohm. So 1 over R, okay, let me just write here. This is for parallel. So 1 over R1 plus 1 over R2 is equal to 1 over 12 ohm. These are the two equations that you're going to be using to calculate R1 and R2. Now you have a simultaneous equation. You need to go and work out what is the resistance for R1 and R2. Now there are very variety of ways of doing this. Okay, meaning you can choose. Some people will choose to. Okay, let's first write it down. R1 plus R2 is equal to 9 ohm, and then the other one is for 12. Okay, 1 over R12. Okay, so R1 plus R2, 1 over R2 is equal to 1 over 12 ohm. So we have these two equations. We need to calculate what R1 and R2 is. Okay, this is basic high school math. So let's start with the second one. Let's write it in a more. Let's call this equation 1. Let's call this equation 2. And let's make an equation 3. Okay, R1 times R2 is going to be equal to R2 plus R1. And that's going to be equal to 1 over 12. This is basically just equation 3, and we rewrote it by finding the common factor. Okay, this is basic high school stuff. No need to rehash it. But what do we know about R1 plus R2? In equation 3, we already know that R1 plus R2 is equal to 9. So we can rewrite this formula, equation 3, as R1 times R2, and there R1 plus R2 is equal to 9 ohm, remember? That's equal to 1 over 12 ohm. Include the ohm there. Therefore, if we rewrite this equation, this one here at the bottom, if we rewrite it, okay, if we rewrite it, we have that, let's just rewrite it, that's 9 ohm over R1 times R2, that's equal to 1 over 12. Okay, now rewriting this gives us that R1 times R2 is equal to 9 times 12. 9 ohm times 12 ohm. This is still, so far, it's just high school math. Nothing new math that any engineer and scientist can do. So R1 times R2 should be 9 times 12. So R1 times R2 is equal to, what is 9 times 12? Let me just check. I just wrote out the skeleton. I did not do the actual 9 times 12. That is 108. So we have 108 ohm. The product of these two is 108 ohm. Now we can form an equation using the sum and then of course the products of these two. First we know that R1 plus R2 is 9, and then R1 times R2 is equal to 108. Just want to check something here. Okay, yep. Okay. Now you should know. Okay, there's following. These answers, this, and then R1 plus R2 is equal to 9 ohm. Remember, you should know that these two are the roots of a quadratic equation. Okay, they are the roots of a quadratic equation. So let's see how would this quadratic equation, what would it look like? It would be x squared, it's quadratic. It will be x squared minus 9x, because that's the sum. It will be x squared minus r1 plus r2. Okay, because this is how a quadratic equation is set up. It will be sum then, and then of course at the end it will be a multiplication of r1 times r2, and is equal to 0, of course. This is a quadratic equation. This is how a quadratic equation is set up. But we already know what r1 plus r2 is. Oh, there's an x missing there. There should be an x there. R1 plus R2 is 9. Okay, we've already established that it's 9. So it's 9x plus. We know that R1 times R2 is 108. Is it 108 or just 118? 108, yes. 9 times 12. So 108. And that's equal to 0. And x will be your two factors. You can now solve for x. X, x. Now what factors of 108 will give you 9? Okay. What factors of 108 will give you 9? In my case, let's check. What factors of 108 will give you 9? Oh, I think I missed something here at the beginning. Hmm. Let me see. So 108, yes, x minus 6 minus 3. 6 and 12, no, doesn't work. I just set up the shadow for this calculation. Let's just see. Clear. I just want to check something. What are the factors? First of all, there's a plus at the end, so both of them will have the sign of the minus. So their product should give you negative 9. Okay, 108. What are the factors of 108? It can give you a 9. Basically, only two. 108. We check. 103. That's 36. It's too big. By 6. 18. 6 and 18 is too big still. Just checking the factors right now quickly. Or you can just plug it into your formula. Instead of struggling like some idiot that like I am, just type it into a formula. They all, let me just see if one of you has solved it. Okay, let me just plug it into a formula and see what I get out. What is x? Okay, so where are my formula? Uh, the quadratic formula. 1b is -9 and c is 108. But I don't like the question that they give us here. But anyway, guys, let me just go and check on this one. I'm not going to hold you up any longer, but I think there is a mistake here somewhere. There should be something here. Hmm, I wonder. But I looked at it earlier, or you can just check these equations here. This is the first way of doing it. Okay, you can solve this equation, but it gives you a point something, which is not what they have. They have only whole numbers here. I'm going to look into that and then send you out the correct answer. But there is another way of doing it, much easier. You can just take all of these. In this case, they give you options. You can just plug in the options and tell you until they tell you which one is correct. Let me just see, quickly run through them. The options should be, if you add them in series, they should give you 9, and if you add them in parallel, they should give you 12. Okay, 5 plus 4 in series is 9, yes. But if you add them in parallel, 1 over 5 plus 1 over 4, 1 over 5 plus 1 over 4, it should give you 1 over 12, which is not the case. So that one is gone. 3 plus 9 in series is not. 3 plus 6 in series is exactly 9. That's 9. So 3 and 6 is an option. 2 and 7 is an option. 1 and 8 is an option. Okay. So B is immediately cut out. Okay. So B is cut out. We've eliminated B. Let's check something. I'm going to give you the full algebraic workout later on. I just want to get to why it gave me those values. Or you can just use a matrix. That's much easier if you've done matrices yet. Okay, so we've already eliminated B. We've eliminated B now. Now we're left with A, C, and D, and E. So let's check all of them in parallel. Okay, 1 over 5 plus 1 over 4 is equal to, it should give you 1 over 12. The common factor there is 20. And it will be 4 plus 5. That's not it. So we have, so A is also now out. Let's time number C, 1 over 3 plus 1 over 6. If we add them together, the common factor is 6. That'll be 6. Okay, it does not have 6 there. If we add them together, it's 1 plus 4. 1 plus 3, sorry. Why is my basic math now letting me down? And that's 4 over 6. And it's not 1 over 12. It's supposed to be 2 and 7. You see, this is the problem I have now. The answer that they tell us it should be 3 and 6, which makes sense. But if you add 3 and 6 in parallel, 1 over 3 plus 1 over 6, you get 2 over 3, that's 6, 2 over 3, 6 divided by that is not 1/12. There should not be 3. I made a mistake here. I don't know why my basic arithmetic is letting me down today. Common factor is 6. This should be 2 plus 1, and that is nothing but 3 over 6. So that's a half. Okay, if you check the next one, number D, this is the problem I had. I'm going to give you the correct answer because I don't think it's here. The next one is 1 over 2 plus 1 over 7. When I did it earlier, I think I saw it, but I just realized the calculation mistake that I did. This then is 14. That is 7. 2 goes in there. And this one is 2. It's 9 over 14. You see, if I work them all out, none of them actually give me what it's supposed to be. Or did I make a mistake somewhere with my calculation? Yes. See, and I agree with uh, Mr. Soweto. None of these can be a solution. You see, because you add. Yes, Mr. Renee also got decimal answers. That's the problem. I also did it right now on the calculator and it got decimal answers. None of these can be the correct answer. Okay. If you use the formula, you will get decimals. Okay. Which means it's none of these. I'm going to go and update this question. But so far, barring the last question, uh, this was a good work set of problems, and I hope when you get to the similar type of problems again, you will know what to do. Okay, I'm going to say all the best for all of you guys, and enjoy the rest of your day. I'm not going to keep you any longer. Those of you who do FVV, I know you have a lecture at 25 past. If you still do that, 25 past 2. Okay, all the best, and thank you. That's all that we have time for today. I'm going to stop sharing now.